Hello everyone, welcome to Summer School Security of Things 2020 and welcome to this talk 15. My name is Darshit Pandya and today we are going to talk about data modeling of field bus systems and its security analysis. Let's start. And before we get too much into the talk, let me tell you something about myself. So, as I said, my name is Darshit Pandya. I come from India. So, yeah, as you can see, this is my natural color, and it's not really tanning from summer. So, I did my master's in electrical engineering from University of Rostock, and currently I am a research assistant. And my major research areas, as you can see, is data modeling, security analysis, and field bus systems. And this is how I generally look, and this is probably how I look when I try a little bit. Today I'm going to talk about my project and the research that I do here in my talk. And so this talk is going to be a journey, I'm going to take you to a journey when I was first told or how I approached this topic. How did I look to the topic? How I introduced myself to the different concepts of the topic. And because we have a wide range of crowd, I'm going to be very general. If you want some more specifics, you can always contact me. My email address is on the first slide of the presentation. Just a heads up, because we have a time constraint. It's going to be a general presentation. As I said, if you want some more technical details on it, you can always contact me. Let's start with the topic itself. Let's start with the name of the topic itself. We see its data modeling of field bus systems and its security analysis, right? So what do we first see? It's something to do with field bus systems. I'm sure we might have, my colleagues might have covered loads and loads of it, and we are going to talk about data modeling most of the time in this talk, and a little bit about the security analysis. The first thing we see in the topic name itself is data modeling, of course. So as I said, we are going to discuss what is data, what is modeling, what is data modeling, the process of how we can create data models, etc. We are going to briefly take a look at field bus systems. We are going to explore the possibilities of how we can create and design data models of field bus systems. And finally, we have the security analysis. So ultimately, we are going to data model a field bus system and perform security analysis of it. So we are essentially going to tie everything down at the end. In the project, I mean not in the talk, because it will probably take me 2 hours to do it, and 2 years to do it, and there's only a 1 hour talk. So yeah, do the math. This is what we are going to essentially talk about. This is a general talk about these three fundamental things, these three conceptual things, and the general outline of the talk is something like this. As I said, we are going to cover data. We are going to cover what is modeling, what is field bus systems, how can we, or is there a way to model field bus system. So we are going to probably eventually have an interaction session of a little while after the talk, and we are going to discuss the possibilities of how to model field bus systems. And ultimately, we are also going to talk a little bit about security analysis. So what are security goals, what is security analysis, what is actually analysis, and how can we perform from a security perspective. So let us begin, shall we? Okay, so first of all, the first topic of data modeling itself. What is data? You must have heard these terms in different context, in different perspective, from different sources. What do you think data is? It's simple. Data is basically just facts. Data is collection of facts, and facts could be anything. It could be numbers, it could be words, it could be different observations or measurements. It could be a temperature report, a weather report, I mean to say. So yeah, it's basically facts, and it's description of things, like how things look, how are things. So and essentially there are two types of data: qualitative and quantitative. Well, yeah, even the quantitative data has further types, but we might not get too much into it. So yeah, qualitative data and quantitative data. Let's take a deeper look into that, because we need to understand that in order to properly understand data. So yeah, let's take a look at qualitative and quantitative data. This is an example. We have a very sweet dog here. It's just looking at you like, yeah, it's very sweet. So let's think from a dog's perspective, and also data could be derivative. So like you have a fact, and based on your knowledge, your previously gained knowledge, you can probably derive some types of other data from already existing data and already existing knowledge. That's what we are going to see in this example as well. So for instance, let's start with like a simple definition of qualitative and quantitative data. Qualitative data provides us with descriptive information about thing or the object which is under the question, and quantitative data gives us the numerical information about it. So these two concepts essentially covers all the things, all the facts, the numerical facts or the descriptive facts or the yeah, almost everything it does cover. So looking at this dog, what qualitative data can we think of? What descriptive information? Okay, first of all, it is brown, of course. Then we discover that okay, the dog is of Bordeaux dog breed, which is essentially a French. And again, this is where the derivation of data comes from, derivation of facts come from, that we know that it is a Bordeaux dog breed, and we know that these breed, the dogs of these breed are really energetic and really strong. And yeah, this photo does not tell us that it's really energetic and strong, but because of our previous knowledge of Bordeaux data, we understand that okay, these dogs are really energetic and strong. Let's look at the quantitative data of it. The quantitative data, well, obviously we are assuming that it's a normal dog, and this dog has 4 legs. It has 2 eyes. It is clearly it can be clearly seen, and because of our knowledge, again, we can derive that these dogs usually weigh around 54 to 75 kgs. Obviously, this dog doesn't weigh that much, but eventually it will. Yeah. So this is the clear difference, and this is the clear concept of qualitative and quantitative data. Yeah, let's go ahead a little bit. Now we understand what is data, but then what is the information? What is information? Like, what is the difference between data and information? Let's take a brief look on that too. There is a very thin line between data and information. So data, as we just discussed, it's facts, right? It's facts expressed using numbers or qualities or any descriptive terms. But what is information? Information is nothing but a collection or a set of data which is processed given a particular context. So it's like, okay, let's take a couple of examples. Let's say you are calling one of your friends in another country or something, and you are just asking how the weather is, and the friend is like, well, it was really hot today. So that is data, because that is a fact. It's a descriptive data because we are not using any numerics here, but it is a fact. So it is qualitative data. But if we collect a set of data, doesn't have to be qualitative, or it can be either qualitative or quantitative. But if we collect a set of data, and if we merge together, we get information. Something like this: the temperature hit 40 degrees today. Given that most of these data in this example is basically numeric, so it's quantitative data. But as I said, it doesn't matter, because information is essentially set of data processed under a context. So yeah, this is the difference between data and information. But just for the sake of simplicity, I might sometimes use information, I might sometimes use data, but essentially I mean the same thing. I mean facts described in numerics or using words or anything. Yeah. So yeah, this was information. We covered data. Let's skip to the model. What are models? So just take a little while and think about it. What are models? And no, I'm not really talking about the models that we see at on different commercials. I don't mean those kind of models. I mean scientific models. So yeah, let's take a couple of examples here. I'm just going to show you images and no text for a couple of slides. So take a deeper look into it. So yeah, this definitely looks some sort of model, right? So yeah, so there's a backbone line, there's some sort of devices here and there. As you can see, there are some numeric identities given to different devices. There are essentially 3 types of devices. There are lines connected to it, and yeah, there's sort of an area of gray box into it. So yeah, this definitely looks some sort of model, right? Yeah, so let's take another example for this for models. Okay, now we have even fewer information than we had previously, right? So there is some sort of a chemical model here. We don't know what each of the vertices is, what the black bonds represent, what the thick lines or the thinner lines represent, what the red dot is. So we do know that this is some sort of model, but we don't know, like we lack some data, we lack some facts about this model. But we do know, we understand that this is some sort of a model, probably of a very complex chemical, but this is some sort of a model. And also the previous example that we saw, that was also that also looked some sort of a subset of a bigger network. Yeah. So what can we now finally say? What are models? Well, I guess looking at the couple of examples that we just saw, we can say that models are sort of a simpler representation of a very complex system, of a whole system, or a very complex phenomenon. Yeah. So if we want to understand something very complex in a simpler way, in a toned down version, so that we can gradually go into the details of it, we use models. This is the most general, most simple definition of it. And we why do we use model? We will obviously eventually discuss deeper into it, but the main motivation of using model is to understand how a system works. So for instance, the first example that we saw, we broke down a huge network into parts, like the gray box, that was the area. So into parts of subnetworks, and we tried to understand how the entire system was structured. And also the second example, as we saw, it was again the structural part of it. We can also probably understand how a bigger system works, how a complex system works by modeling it. Yeah. So these are the 2 main motivation for creating models. Okay. So now, keeping this thing in mind, let's think about how can we, like, what are models made of? How can we, like, just look around yourself currently. I'm hoping you guys are making notes. So you might have notebooks. You can probably structurally describe the notebook using pages or the pens or the external cover, soft cover. You are probably using pen, so you can structurally break down the pen. You can divide it into parts. You can understand its working by breaking down to its elements, to its core elements. And yeah, ultimately you have broken down a complex system into simpler parts, which is basically modeling. To make it more realistic and more practical, let's think of a common thing. Yeah, let's take an example on this. So in this summer, everyone is At least in Europe, everyone is on their cycles, on their bicycles, and yeah, this is the most generic bicycle photo that I got on the internet. And let's try to create a model together of this bicycle. Yeah. So what did we study from the previous slides was basically a model is used to describe or represent a complex system into simpler parts. And how do we do it structurally with this bike? So first of all, let's break down its structure. The two main things we can see in this bike are its frame and its wheels. There are these two things in the bicycle, like the complex system that is this bicycle. And if we again break down the frame, because there are several parts of the frame, yeah. If we break down the frame even beyond this, we can see that there's a saddle, there are handlebars, there are pedals and crank, and then there's this chain which is a part of the frame. And again, further, if we go and break down the wheels, there are obviously tires and tubes and spokes and brakes and everything. Yeah. So what did we do? We looked at a system as a whole. We tried first to divide it structurally. We tried to divide it into the most obvious, most basic parts, because we can see there are only two distinct parts structurally of the system. And then we further divided into it based on its application, because saddle, and also we agreed that okay, we are calling it saddle and not seat or anything else, right? So that's what essentially modeling is. This is how the process goes. We will summarize the process later on, but yeah. So this is how we do modeling, and this is how we break down the system structurally. Let's go a little bit further. So let's say there's a kid and he is asking you what is a cycle and how can we drive it and what is it used for, etc. Well, we know what is it used for, and we have also broken it down structurally. We have advised the kid that okay, this is what these are the parts of cycle. But the kid is like, okay, now how do I ride it? How do I drive it, right? So now we take a look at the functional breakdown of how a cycle works, because as we remember from the modeling side that slide, that it is essentially used for describing a system, like breaking down system into its part, and describing how a system works, right? So let's look at the functional aspect of it. So while explaining to the kid, you say, well, it's pretty easy. You sit on the saddle, you sit on the seat, apply force to the pedals using your legs, of course, which pulls the chain, and essentially it rotates the wheel. And yeah, but then this is not enough, right? Because with this you can also drive the cycle in the gym, the cardio exercise that you guys do or try to avoid. Yeah, so what else is there? We also have handlebars, we also have brakes. So what have we done here? Let's go back a little bit and try to understand what have we actually done here. We first of all saw the structural part of it. We first of all saw the structural division, how we divided it into different parts. We looked at the most essential members. We looked at the most essential categorization breakdown of the system, which can also be called entities, like just a general term, entities. We might also, if we want to go deeper than this, we might also take a look at what are these made of, like what is a saddle made of? Is the seat made of leather? Is the seat made of plastic? What is it made of? Similarly with the chain also, right? We can also go, what is the quality of the chain? Is the chain too long? Is the chain too weak? What like these things, these properties, these essential properties of entities will define the quality of how the system will work. Yeah. So it's not only important to break down the system into its essential part, but it's also important to list down the properties of these entities, or we can say the attributes of these entities. So these could be the structural things like entities and attributes. So now after that, what did we look? We looked at the functionality. We broke down how does a system work, how does the bicycle work, and we looked at the functionality. And by the way, all of these are facts. If you see, just like what we did with the dog, we saw that okay, it's brown, it has 2 eyes, and it has 4 legs, etc. The same thing we did with the cycle also. We broke down with our previous knowledge, and these are all facts. So we are essentially making a data model of the cycle. And yeah, let's now take a look at the functional breakdown of the cycle. What did we do? We used the same entities as we had defined in the structural breakdown, and we tried to link everything. So we use the pedals, we apply force on the pedal, we sit on the saddle, we pull the chain through the pedals, and which rotates the wheels. And also this makes the bicycle in the motion. But how do we control the motion? If we want to control the direction, we can use the handlebars. If we want to control the speed, the velocity, we use the brakes. So even in functional breakdown, there is further breakdown possible. So what we are essentially doing is we are using the entities that we defined in the structural breakdown along with its attribute, and we are trying to establish some sort of relations to it. We are trying to establish some sort of link that exists between these structural entities, and we are trying to understand how these entities work together and basically the entire system function. And this is just a small example which everyone knows, and this is essentially how every other system in the world, be it how much complex it is, this is how it works. Because essentially what you do is you break down an entire system into subsystems. You try to create model of it, you try to gain better understanding of it, you try to divide it into entities, you focus on the attributes based on the context there, based on what it is used for, and then you try to establish links and relations between these entities, and try to anticipate the behavior of the system. So this is before designing and after designing also. If we are analyzing a system, we can do the same. So yeah, these are what models are made of. We establish relations between entities, and entities already have sort of inherent properties which are attributes. So what have we learned from this? Any model has have these three most important ingredients. Let's go back a little bit. Structural breakdown, the most basic elements. What are these most basic elements? They are entities or objects. As we saw in the dog also, or as we saw in the cycle also, we had these most basic structural elements. Then what are these elements made up of? Like what are the properties? So those are the attributes of these entities which comes along with the entities. And this was the structural parts. Like we understand that the entire system made of these elements or these entities, and now in order for the system to run, we have to think of the relationships. We have to think of the dependencies between these entities having these different attributes. So then we think of the relationships between these entities and attributes. So these are the three most important ingredients of any model. So then the next thing we look at is the context. As I said, because modeling is used in several different aspects, like we can use it for designing a system, for simulating or for anticipating how a system will work, or we can use it for analyzing a system. So depending on the context, the structure and details of a data model changes. So while creating these context dependent data model, we have to focus on two most important things: syntax and semantics. If we don't understand the semantics, if we don't understand what a saddle is or what a crank or what a chain is, we are not going to understand the data model. So we have to agree upon the semantics. Syntax I'm going to discuss in a little in my later slide, but we have to agree upon the semantics of the system. So what have we learned? Three most important ingredients in data model: entity, attributes, and relationships. And the two most important considerations while creating a context dependent data model is syntax and semantics. Okay, what do we do with this knowledge? We try to create a data model. Of course, we graphically sort of created, or textually we sort of created a data model for the cycle. But how data models are actually created? First we list down the semantics. We don't want any sort of misinterpretation while we are creating a data model. So we focus on the semantics first. Then we define the entities. Like once the semantics are pretty clear, we define the entities and the different attributes of these entities. Like what are these entities? What are the properties of these entities? Because these two together plays a major role in creating the most basic structural element of the system. And then finally, we establish relationships between them so that we can finally model the behavior or the function of the entire system. So yeah, this is while creating a system. This is while designing the system. But what we did with the bicycle was we broke it down. We analyzed the bicycle, the structure of the bicycle, the working of the bicycle, and we actually did the same thing. So yeah, and finally, as I said, all these can be done graphically. The first example that I showed you of the subset of a network, that was basically a graphical representation of a network, of a building automation network. And yeah, obviously it's not the same. Like the device does not look green, and yeah, but this is how you create a data model graphically. So these three parts could be done graphically. Then what do? We then agree upon a syntax for the data model. Like, okay, we understand the semantics, we have the entities and attributes, we have linked up all the entities, and we have established the relationships. But we can do the same like in English or in French. And yeah, because these are the languages that we use to communicate with humans. But we are not communicating with humans. The further applications are on a computer, are on a machine. And what does a machine do? Like what does the machine understand? It understands only some languages, like mostly binary, but there's also a higher abstraction of binary, and we can use those abstraction and we can use them as a syntax. So we finally agree upon a syntax, and based on the agreed upon syntax, we can create a machine interpretable, machine readable format for further processing and applications. So yeah, these are the fundamental steps of how do we create a model. Okay, and what do models actually look like? Again, I'm not talking about the TV models or the movie models. I'm talking about the data models that we talked about, that we saw. So the graphical versions was I already we already saw the graphical versions. There were those black dots with incomplete information, and there was the subset of the network. But how does, as we discussed in the previous slide, how does a machine readable format of the model look? So yeah, I'll show you a couple of photos. This one is again. So this is the syntax I was talking about. Each and individual line is a different entity, and it's a unique entity, and it has an identity called hashtag. Like the left side of the file that you see, of the screenshot that you see, it's its own identity. And then there's the type of entity. What type of entity is it? And then you can also see in the brackets of every entity there are there are numbers just like we have on the left hand side. So what does these number indicate? These number indicates the relationships between these entities. Like number 453 has relationship with 3 different entities: 448, 452 and 19. Similarly, 452 has only one relationship, that's with 450. And how many relationship can one entity have also depends on its attributes, which are again listed in all the entities, as you can see. So yeah, this is one of the examples of how a machine interpretable data model look like. But like, we don't have to understand it, we don't have to comprehend it. Why? Because this is for the machine to interpret, and this is for the machine to do further processing and apply. Let's take a look at one more example, which is a bit simpler. Oh, by the way, the previous example was a data model based on object-oriented modeling. We'll talk about it a little bit. And now the thing that we are looking at, it's basically XML. You guys might have heard about it. It's a very famous data model. Again, this is also a machine interpretable, machine readable data model format. But as you can see here, we can still somehow figure out, because the syntax is a little bit readable, we can still somehow figure out some basic elements, and we can still somehow try to understand the relationship between the different entities in these files. So yeah, but the first time we saw it, we were not able to understand it. We were not able to comprehend it. Why was it? Why do you think was it? Yeah, of course, I already told you that these are machine interpretable, but we also do not know the actual syntax and semantics of this model. If you remember, how do we create a data model slide? The first point was we have to get our semantics right. We don't know what any of these terms mean, and we don't know what does it represent. We know that it's a fact because it's a data model, and data is essentially facts, but we don't know how the facts are being represented. So we don't know the semantics of it. And also, we can probably understand the syntax of it because these are quite famous syntaxes. So we can probably break it down using some tools, but still, without semantics, we might not be able to understand what any of that means. And yeah, again, the same reason as I said, because these are machine readable codes, machine interpretable data models, these are mostly meant for machines and not for humans. So yeah. Now, yeah, as I was saying, the previous examples that we saw, these are the well-known examples of data modeling. So the first one we saw was object-oriented modeling, which is very famous and very popular amongst software developers and in computer science in general. So while designing a software or while designing a system, object-oriented modeling is being widely used. Then there's entity relationship modeling, like the name itself has that entity relationship modeling, which is again famous in database design. And then finally there's XML modeling, which is again essential for information exchange. Again, information exchange between machines, because these are all machine interpretable models. This is the last part, as we discussed in the how do we create a data model. So this is the syntax that we agree upon. This is the converted machine interpretable data models that we also saw in the previous slides. Yeah, so I guess that ends the how do we create or what are models made of part. And yeah, let's look at the applications. But I guess I have covered most of it while speaking. So yeah, models, as we have understood from the very first slide, models are basically used for breaking down the system, to understand how a system is structured, to understand how a system might behave, or what is the working of the system. And by understanding this, we might have a better understanding, we might comprehend the system in a better way. And because we understand the behavior of it, because we can probably eventually anticipate the behavior of a complex system, we might be able to make a little change and make better updates if the system is like not running it, not working as expected. Again, the further applications are so many. Like we can simulate bigger systems, like for instance, nuclear experiments or a rocket launch. These are very expensive scientific work, and we probably cannot experiment in real life. So what do? We make data models out of it. We try to feed these experiments or feed these data models to a computer, and we try to simulate how it might work in real life. And in the same way, we also, as I said, we also analyze a system. We break down, we try to understand the system, and that is what we are going to do eventually. We'll discuss it in the further slides. And finally, as I said, information exchange, XML is a great data model syntax for information exchange. Information exchange is also constantly happening currently. Like there is some information on this slide, there is some information on this video, and you probably downloaded it on your local PC, or you are watching it online, and there is constant information exchange between these two machines, like your laptop or whatever device you are watching it on, and the source or the website from where you downloaded it. So this also contains data model, the information exchange part. So this is kind of the end of data modeling part of the talk, and the summary is in front of you. There's data, there's models. We also looked at the basics of two types of data, qualitative, quantitative. We also looked at a model, what are models, the three important ingredients of a model. How can we try and create a data model? How can we break down a complex system or a complex thing into simpler things? And how can we establish relationships between the entities to see how a system works? We also discussed about the syntax and semantics. We also discussed about how machine interpretable codes look like, and how is it different from the graphical code, the graphical data models that we try to create, or the textual data models that we try to create. And finally, we also looked at some of the applications of data modeling. And with that, we move ahead to field bus systems. I'm pretty sure these systems are being well covered by my colleagues in the previous talks, and this is because this is extensively what our group work upon, and I have, over the time, I have created like an evolving impression of field bus systems. Like earlier, how I understood these were a bit different. Now, how I understood and how I look at these concepts are a bit different. So instead of diving right into it, let's first take a look at what we already know, right? We are well aware of internet. It's been here for quite a while. Internet, interconnected networks, as we all know. So there are little networks, and then there's a network of networks, and then there are again network of networks, and they're all interconnected, and that's essentially internet for you. And with internet, what are the regular applications that we do? Like you are streaming this video, you downloaded this video, very high quality, high resolution video. It takes a lot of data. You stream Netflix, you stream YouTube, 1080p, 4K. I don't know. So basically, it deals with high quanta of data, right? High volume of data, and the temporal requirements are also not so strict. Like you won't lose your mind if the video, like the buffering, takes 1 second or so. It's good to be real time, but you won't mind. It's okay to have a little bit of delay. And the geographical reach, of course, it's worldwide. So you can essentially talk to your talk to your talk to your friends or your loved ones, like in two completely different corners, and you can still talk almost real time with decent quality. So yeah, the geographical reach is also worldwide, and yeah, long distance communication is essential. And yeah, the determinism of the system is very low, because by mistake you clicked on a video, and the system did not know, like that wasn't deterministic. Like it's not. What does a system determinism means? Like the system almost always knows what is the next event going to be, and that's not the case with you. That's not the case with internet. Why? Because not every person waking up in the morning watches the same video at the same time. If that were the case, then the internet would have been so much of better quality, and the speeds would have been faster. But that's not the case, because the system is not deterministic. And finally, the main motivation behind internet was human interaction. Like, yeah, you are interacting through devices, so essentially it's the devices that are interacting, but it is meant for humans. Like, it is, the medium is the devices, but it's done through the humans. The humans are what yeah, controls, or the humans are the environment for these systems. But how about the machine interaction? What about when devices start interacting? What will they talk about? What if because the topic itself is like the topic of the entire summer school itself is security of everything, right? So everything is also devices. Devices are everything. Yeah. So basically, what about these machine interactions? How are they helpful to us? So let's take a look on that. So first of all, machine interactions are mostly used to provide facilities and increase comfort and luxury locally. So just think about the elevator in your building, or think about the occupancy sensor in the mall. So like as soon as you go near the door automatically opens. So this is essentially a machine interaction. It provides you facility that it opens doors for you, instead of employing a security guard as we did in the traditional period. And it increases the comfort. Like yeah, there are segways. You don't have to walk anymore. The bicycles that we saw, the functionality has almost changed, because there are battery operated bicycles. If you are on upslope, yeah, if you are on a slope, you don't have to pedal anymore. The battery will take care of it. So yeah, essentially these are to provide you facilities, provide you with luxury and increased comfort. But the important thing is locally. It cannot be like you are in Australia and your friend is in Canada, and you want to do something for him or her. You can do it through internet because it has global outreach, but you cannot do with these machine interaction, because they operate locally. And examples, yeah, as I said, the occupancy sensor to door. We also have Alexa. Yes, I agree that variations of such systems like Alexa, they do work on internet, but again, the important thing is mostly they usually they work locally. So yeah, as you can see from these examples, these are essentially, yeah, the environment. Yes, the environment is changed through human interaction with the environment, but essentially an occupancy sensor senses, it interprets that okay, there is someone in this room, or there is someone approaching the gate, and it then communicates with the door that hey, you need to open the door, there is someone coming, or hey, you need to switch on the light, there is someone coming. And even with Alexa, if you call Alexa and you tell her to switch on the lights or switch off the lights, it communicates directly to the light and tells it to turn it on or turn it off. So basically, yeah. So these are understanding the device-device interaction, machine-machine interaction will give us a better understanding of field bus systems. Okay, further we can see these are called field devices. We have to remember this because these are on the field. Well, yeah, these are the devices that directly communicate or directly interact with the physical environment outside, and yeah, provide us with facilities and comfort. Most of these field devices, most of them they are used in automation systems, of course, to automate the systems in manufacturing industries. Yeah, there was an amazing show on National Geographic. I'm not sure if you have seen, called Mega Factories, and yeah, they had a really cool documentaries on these manufacturing industries and how automation was mostly used and robots were mostly used in making these industries, in the functioning of these industries. Then yeah, even domestic applications as we saw with Alexa, and yeah, now even home automation systems and building automation systems are in the trends right now. Then yeah, there are also automation systems in ship and aircrafts. And yeah, the most important thing here to understand is the system is local. It's not outside a physical boundary, right? Even if you look at domestic applications, so that's a home that is confined within a boundary, like a physical concrete boundary. Again, automation systems in ship and aircraft, it is moving, but it is still confined. The devices or the system, they work inside a confined area. Yeah, and now since we now understand a little bit about the applications of these systems and about where and how does it work, like a little bit, we can also pen down all the things that we did for the internet. Like the data requirements here are pretty low because the devices don't really share YouTube videos with each other. They also do not stream Netflix videos, like yeah, they also don't stream Game of Thrones or don't get upset over the ending. But yeah, anyhow, the data requirements here are pretty low because they only share signals and statuses and commands. The temporal requirements, yeah, as you might have noticed in the applications, these are used in ship and aircrafts and manufacturing industries where so these are called critical infrastructures, by the way, because any small temporal glitch or any small temporal here or there, and it could lead to fatal problems, fatal events. So the temporal requirements are very high, which is unlike internet and very contradictory to internet. Geographical reach, as we discussed, these are mostly confined within a physical boundary, like an aircraft or a house or an industry. They are confined within a boundary. System determinism very high because even today, as you know, like with Alexa or with any of these domestic systems, you can only work with some commands, like very few commands. So there are fixed predetermined commands, predefined commands that the system works with. So the system determinism is very high. Same goes with industries also. Like it knows that the next step is going to be this. Like whenever you start a system or whenever you start manufacturing something, it knows the next thing is going to be this. And yeah, and since they are local systems, traditionally these were physically isolated from other networks. So yeah, this is important because this is a changing trend or rising trend in the past few years. Like earlier, if you want to know what is going on in a system, in such isolated system or in such a local system, you have to go there and you have to try to like look at it from a higher abstraction, and you have to see at each and every parameter. But now with the increasing trend of remotely monitoring it, remotely controlling these fields, like manufacturing industries, or constantly monitoring the aircraft level or the sea the ship route or something like that, we have to create it to other network. Yes, internally, still all the devices are connected using these field bus systems, but once you have to connect it to, like, once you have to outreach to a global area, like once you have to increase the geographical reach, you have to connect it to other networks also. But traditionally, we have to understand they were physically isolated. They were not connected to any external networks. Yeah. So basically, these specialized communication infrastructures which connects all the field devices, the communication backbone, as we saw, is basically the field bus systems. And yeah, uh, these field bus systems are designed in such a way that they successfully fulfill all the requirements that we saw previously for these systems. Like they have lower bandwidth because the data is not so bulky. It has real time. It fulfills real time applications. It tries to fulfill real time applications, and yeah, it's a little bit different from the traditional internet IT network settings. And yeah, and as I previously mentioned, these were physically isolated systems, and traditionally these systems were point to point. So in the previous examples, we saw this with sensors and doors, or Alexa and lights. So traditionally they used to have point to point connections, like this device connected to this device, and that's it. These two devices are then not connected to anyone else, unless this device also controls other devices. But still, these used to have point to point connections. And now with field buses, we have a bus kind of a system. So think of it like an analogy I could use is like a cab service and a bus service. Like the point-to-point architecture is kind of a cab service. So you arrive at a new city on train, and from the train station you take a cab to your hotel, or yeah, to your hotel. So that's a point-to-point service. Like you from the train station you went to the hotel. But if we think of the bus architecture, it's exactly like your city bus, or the trains that you take, like the subways or something. You from the train station, you will eventually go to a nearby bus station, or a train station where you are supposed to stay. And it doesn't matter where you want to go. The bus or the train will take its predetermined path. So that's that's how the bus architecture also works. So it connects all the devices, and the message is supposed to wherever it is supposed to reach, it will reach through this bus architecture. Of course, there are different variants of it. You must have heard so many, depending on the application domain. Of course, there must be CAN, there must be KNX systems, and yeah, others too, Profibus, Profinet, and yeah. So there are different systems based on this, but yeah, this is the most basic properties or requirements of field bus systems. Okay, yeah. So let's take a little break and think, and take a step back and think about this. Like, this is a machine-machine interaction, device-device interaction. It's kind of similar, as I said, to the Alexa lamp analogy, or the sensor and the door analogy. And yeah, it's kind of like a local network, as I said, being confined in a physical boundary. Okay, like think of it like this. Like, we only have one room for now, and in this room we try to automate a couple of things using Alexa, right? So in one room we can still control these. But what if we have more rooms, and what if we need more devices, because one Alexa cannot really react to someone who is in a completely different room. So we'll need more devices, we'll need more communication devices, we'll need more other kinds of devices. So let's first take a look at what types of different devices are there in such systems. So we have, first of all, sensors. Of course, it detects changes. So if we think about the Alexa example, Alexa itself is a sensor because it hears the 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 data or the change in environment. It detects the change in environment because currently it's silence, and then we say, hey Alexa, and it listens to that hey Alexa. It detects the changes in the environment. And same goes for sensors also. The occupancy sensor, it detects no one. Hey, there's no one, and then suddenly there's someone coming. So there was a change in environment, and it senses. The sensors sense the change in environment. And then using the device-device interaction through these field bus systems, we have actuators which actuate the things which enable the changes in the environment. So the sensors hopefully captures the change in environment, and the actuators actuates the expected changes in environment. Like a temperature sensor might sense that, hey, it's getting pretty hot in this room, and using the field bus, it tells the actuator that, hey, it's getting pretty hot in this room, and actuator is like, yeah, you are right, it's getting pretty hot in this room, and then it'll try to decrease the room temperature by I don't know, blowing out cold air. Or yeah, we probably also should make a data model for air conditioning system. Okay, yeah, so sensors and actuators. But yeah, this seems to be a pretty point-to-point kind of connection. There must be some other way to handle more sensors and more actuators from one single device, right? So yeah, there are controllers to do this. What does a controller do? It takes sensors. It takes the sensors readings or sensors measurement, and it directs the actuators according to the sensor data. Again, the controllers are responsible for controlling the behavior of actuators, of many actuators, based on the readings it gets from many sensors. So it has predefined logic in it for many different sensors and many different actuators. For instance, if we have multiple rooms, or if, let's say, if we have a university and there are multiple rooms on the same floor, of course, and again, multiple rooms will have multiple sensors, like temperature sensor or occupancy sensors, and again, it will also have multiple actuators. So what will the controllers do? It will take multiple readings or multiple measurements from other sensors, and it will actuate through multiple actuators, and the logic will define where the sensor readings are coming from and where it is supposed to actuate the real thing. Yeah, so these are the three main elements or three main types of devices which essentially bring changes to the environment. But what connects them? What are the devices that enables this communication? So then next we have communication devices, of course. So if you have already learned about this in previous slides about KNX systems or such field bus systems, you might already be aware of systems of devices like couplers or repeaters or routers or something like that. So these are essentially the communication devices which enables the communication. So they do not directly influence the environment, but they are responsible for communicating the messages to and fro from the devices which directly influence the environment or which get directly influenced from the environment. Yeah. And finally, to connect everything together, we have links. We have different mediums, different physical medias that connect all these devices. Like, could be from a sensor, it might connect to a communication devices, which then directs this message or this data, because it's a fact, because sensors will tell you the facts that, hey, it's 27 degrees and it's pretty hot, and from that communication device it will be rerouted to a controller, which then interprets the data that, hey, it's pretty hot, and then essentially it will ask the actuator to decrease the room temperature, probably through a communication devices, and all this communication happens and is realized through a communication link. So yeah, these are the main different types of devices, and like yeah, as we broke down the structure in the bicycle, this is the structural breakdown of bicycle. Yeah, and yeah, clearly this is a distributed system, as we discussed in the example of the university, how there are different rooms, different sensors, different controllers everywhere, and different actuators. We can say that this is a locally, because again confined within a boundary, it's a locally distributed system. Yeah, and one way to describe this distributed system. Okay, let's first think about it. So there are different devices in different rooms. They are all distributed, but again within a boundary, and they are all connected through two different communication elements, so communication devices and communication links. How can we describe this kind of distributed system? We know it's in a confined boundary. We know it is distributed. We know there exists relationship between these entities or between these devices, because sensors, controllers, actuators, and the enabler is the communication links and communication devices. How can we describe these systems? Simple. As we in the previous slide, as we divided, like with using two different colors, we divided these systems. The devices that were directly getting influenced or directly influencing the environment. So those could be, yeah, those are our devices, and then the others are the network devices, or which are responsible for the network behavior, or yeah, for laying out the network or for enabling the communication. So yeah, we can describe them separately, like describing the devices and describing the network. And if we take a look at the traditional IT networks or the traditional description of network, one way to describe network is using topologies. Okay, let's take a deep breath, because we have literally established that these are distributed systems. We have introduced one way to describe these systems, like just like we did with the bicycle, that okay, structural breakdown and then functional breakdown. So here we have describing devices, and then we have describing networks, and then we have also introduced topologies. So let's take this one thing at a time, and let's discuss what are topologies. So topologies are basically graphical representation, and yeah, it also has a little bit of math behind it, but don't worry, we won't go much into the math part of it. So yeah, these are basically the graphical representation of a network. So there are nodes and there are edges. So of course the nodes are responsible for the messages, and the edges are responsible for carrying the messages, or for taking the messages from one node to another, or yeah, however is expected. So these are basically topologies. This is the most basic example of topology. So it's kind of a graphical, we can say it's a graphical model of a network, but it's a structural model, because we can only see, according to the basic definition, we can only understand how, like what devices are connected, but how are they connected? We might take a little, we might have to take a little deeper look in these topologies, or the type of topologies. So there are three types of topologies. There's physical topology, logical topology, functional. Of course, there could be other types of topologies too, depending on the context. But here we are looking essentially at these three types of topologies. Okay, the first topology is the physical topology. How is the network laid out? Where are the devices? Which room has which network? Okay, first of all, before making the data model, we also remember from those slides that we need to first clear out the semantics of the data model. What devices are we calling devices? Are we calling all of them devices, or are we calling one of them as automation device, are the communication devices. So how are we calling the wires or the physical media? Are we calling it links or edges or physical medias or wires or cables? So we need to clear out the semantics first, and once we clear out the semantics, the same thing we did with the cycle example. We break down the network structurally. So the physical topology deals with that only. Like as I said, the network is distributed. It is distributed, but it is in a confined space. We first structurally break down the confined space so that we can understand where each of these devices lie, like in what confined space area does these devices lie. If you take a big building example, a university example, what classroom, what room, what cafeteria area, what corridor does a specific device lie, and that sort of defines the physical topology. And then the next thing we look at is the logical topology, because from a network point of view, because topology, as we know, is essentially nodes and edges. So from a network point of view, or we also saw in the screenshot in the data modeling slides, like the example of the data model, from a network point of view, each device will have an identity, or an address through which we can address the device. But we can understand, or we can recognize a device through its address. And if there is information or data flowing from one address to another, we need to understand how the route, what route is being taken for the message to flow, or for the data to flow. And that could be described using the logical topology, like the hierarchy of devices. There could be hierarchy of devices that there could be controllers, and then the other hierarchy, like the lower hierarchy level, could be the sensors and actuators. And so all these things, all these properties are defined using logical topology. And finally, the functional of it. So just like in the cycle example, we broke down the functional part, or the behavioral part in the letter, in the letter section, right? In the letter breakdown. So once we have, so this is how also probably we design a system. We distribute the devices into the different rooms in the confined space. Then we establish the links between them, and we also establish that, okay, what information will flow from where, what communication devices will get included in different device interaction. And finally, we define the functional part of it, the functional topology, what two different devices are connected to each other, or what two different devices will interact with each other. So how are these devices connected functionally? You have to push the pedal to pull the chain to pull the wheel eventually, which will also rotate the front wheel. So the same goes with the functional topologies also. We do the same with devices also. So these are the three main topologies through which you can. So the advantage of describing field bus systems using topologies is, the earlier method that we saw for describing this system was to divide this description into device description and network description. But the idea behind using these topologies is to somehow integrate this device description and network description. So all the device attributes and all the small device properties will be included somehow in these topologies, and that's which is essentially the network description. And that's what we are trying to do. We are trying to, I am basically trying to research, or trying to find a solution for this. How can I integrate these descriptions? How can I describe the essential features of a device, of a sensor, or an actuator, or a controller, or a communication device also? Of any device, how can I integrate the attributes or the important properties of this device into the network description? And yeah, how can I represent the entire system using these three topologies? Yeah, and yeah, I also have to look into the details of it. What kind of, what depth of detail do I need to take a look at, or what kind of syntax should be used, as we saw in the data modeling slides. So yeah, because there also we saw that object oriented designs are used for different kind of applications, and XML are used for information exchange, etc. So yeah, this is essentially my research. Yeah, so this is essentially the part of my one part of my research about how to describe the systems using these topologies. And yeah, so that brings us to the end of fieldbus systems. I'm sorry I did not go too much into detail about this fieldbus systems, because I'm assuming that you guys are well aware of it because of the previous talks and workshops. So yeah, as we discussed, fieldbus systems are the backbone for communication for these devices, and several types of devices are used in these systems. We repeatedly discussed that also, and the traditional method of describing these systems is through, like, yeah, using two parts: describing devices, describing networks. And the current research interest lies in describing the entire system using these three topologies. Oh yeah, and also one interesting thing could be we can introduce one more topology, or we can take like one less topology and try to describe it as efficiently as possible. Now, why are we describing it, or why are we putting so much effort, or why are we, yeah, putting so much effort into describing these systems differently? Is the major motivation is security analysis. But before diving into that question, that why do we need this, we are first going to discuss about the security goals of any system. If you have been um, if you have been in in introduction to any sort of security principles of any systems or of traditional IT systems, you might be aware of these security goals, these three famous cybersecurity goals. It's confidentiality, integrity, and authentication. So yeah, again, I'm pretty sure these topics would be covered by my colleagues, but let's take a brief detour on this. Confidentiality deals with, so the, because we are discussing about the field bus system, so I'm going to consider the field devices interactions. Yeah, so there are two devices. Confidentiality means that when two devices interact, they have to, like, the confidentiality security goal states that the interaction should be confidential. So there's not a third entity, or there's not a third device that reads or that goes through the content of this interaction. For instance, there could be a controller in between, or there could be a communication device in between, but the goal or the function of the communication device in this case is just to route the messages, or just to forward the messages to the specific device or the destination device, and not to meddle through the content of the message. Integrity, also the security goal of integrity, meaning that if a message, like if there are again two device interaction, if the source device sends a message to destination device, and the destination device receives a message that says that, hey, I'm a message, and the source device sent this message to you, the integrity security goal states that it should be the source device only, and it should be confirmed, it should be assured that yes, the message was actually sent from the source device, and same goes with authentication also. Like the authenticity of the devices, the authenticity of the messages or the interaction between them. And because we are working with a system with special requirements, as we saw in the previous section, we also have one more security goal called availability. So yeah, it's not anymore three famous goals. There's fourth one now, and that's availability. Why availability? Because, for instance, you are in a plane, and there is some problem with one of the security goals in the system. Then availability should be one of them, because availability is really important in such critical infrastructures in manufacturing industries or in planes or something. So yeah, availability also. So these security goals are basically called CIA triad, but because there's availability, so we are going to talk about CIAA. Yeah. So basically, how do we define security risks? So any circumstance or any configuration that hinders a system's ability to achieve any of these goals or even one of these goals, then that circumstance or that situation or that configuration of the system is essentially a security risk. So when we say that okay, there's a vulnerability in the system, or there's a security risk in the system, this is what we mean, that this situation or this particular configuration of the system is in the way of the system's ability to achieve these goals. Yeah. So this is the basic definition of security risk. So it is important to understand what are these goals and what is security risk before getting into the security analysis part. Okay, now let's understand. And now that we have understood about the security goals of the system, now let's understand analysis. What do we mean when we analyze something? So yeah, as we have discussed earlier, using the bicycle example also, we break down the system into its basic elements. We try to understand how each of them relate to each other. We try to understand how it works, how the behavior changes. So we analyze something. And what do we do when we do security analysis? Well, basically we do the same thing, but we try to analyze if we have any security risk situation. So like we try to go through each and every configuration. We try to, because we are also trying to understand the different configuration of the system. We are also trying to understand how the systems might work, how basic elements are tied up with each other, how the states of basic elements or changes through the change in the system or through the functioning of the system. We are trying to analyze if there exists a potential configuration which challenges the ability to reach the security goal, to reach any of the security goal of the system, as we discussed in the previous slide. Yeah. So this is basically security analysis. How can we use data models for this? Well, the analysis part also already felt like creating a data model, right? Like we have to create data models. So we have to break down the system. We have to again define the semantics. We have to break down the system into entities, and we have to think and we have to consider those attributes of entities which through which security analysis or through which the security risk part of the system becomes natural, or it becomes obvious. It tells us that okay, if you are using this entity related to this entity with these attributes, then this configuration makes a high security risk situation. So that's where data models can be really helpful while doing a security analysis. We have to understand entities and attributes. We have to understand the system through these entities and attributes and their relationship, so as to create different configuration, or so as to analyze, or so as to go through every possible configuration of the system through its working, so that security risk becomes apparent. And so the previous field bus system and data model discussion was about how to describe the field bus systems using these topologies: physical, logical, and functional. And now we are not only thinking of describing these systems using these topologies, but we are also thinking about, while we are describing these topologies, we also have to focus on how it can represent the configuration, or how it can describe the configurations that could take us to potential security risk, that could give us some idea of potential security risk. So again, the physical, logical, functional topologies could be really helpful in describing the general, the overview system, the context-free description of the system. But now we have a major context. We have security risk. We have to think of the configurations, or the attributes, or the details, or the relationships established, and we have to think of the configurations that this will eventually lead to, so as to predict the security risk. So this is how we can use data models, or this is how we can think of using data models and topology descriptions in order to predict security risk of system, or configuration that will lead to security risk. How can understanding attacks help us into this? Okay, so let's imagine that you have been robbed, like your houses have been robbed. God forbid that doesn't happen, but let's imagine that you are been robbed, and now the police comes to your house, and they are trying to question you that, hey, when did you leave, when did you come back? So they're trying to set a time frame, like from when to when the robbery might have happened. They might analyze the other CCTV footage or camera footage around your house to probably try and understand who the robber might be. So all these things together might help the cops, or might help the police to find out, or to track down an attacker. Same goes here too. Like, we have to understand attacks in order to understand security risk, or in order to understand how an attacker might exploit a security risk, or might exploit a situation so that it potentially becomes a security risk. So that is important. We can learn a lot from previously occurred attacks, as we talked about in the robbery example. So what do is we take the examples of previously occurred attacks. We go through the situation, or we go through the configuration of the system when these attacks occurred, and we try to look at the entities and the attributes of these entities. Like, a device could be an entity, for instance, and what are the configuration of a particular device at that time, and the relationship, like from where could the attacker might have entered the system, or from what is the medium through which the attacker attacked the system. We can try to understand that, and then we can try to implement the same idea, or we can try to focus on the same attributes or the same entity relationships in other data models, and we can try to predict a potential risk if there is in a system. So that's exactly what the slide mentions. Like, we have to closely observe the exact system configurations, and that could give us a lot of information on risk and the potential risk further in other data models or in other systems. So this is how understanding attacks can be helpful in order to predict potential risk. So now we are tying everything together. We are tying the loose knots together. So what is what is my essential research? Like, what did I mean when I said in the earlier slides that we are going to talk about data models and field buses and security analysis? And what does the topic of the talk means? Like, data modeling, the field bus systems, and security analysis. So this is what it means. We need to create data models. Well, of course, the detailed part is in terms of topologies, and we need to include the device information, the network information, everything in these topologies for the field bus systems, but that's field bus specific. Yeah. So we need to create data models for field bus systems such that we can discover most of the potential risks present in the system. We understand what data models are. We understand what field bus systems are. We understand probably how can we create data models for field bus systems, traditionally describing a device, describing a network. Now we are focusing on the topologies part. We are trying to integrate the device and network information, and we also understand what are security risks. So we understand the security goals, any configuration or situation that challenges these goals or risk, and we also understand that we need to discover or we need to predict these security risks. How? By looking at how the field bus systems are structured and how does it work, and while working or by the way it's structured, does it give us a configuration that might lead that is a potential security risk. So that is what we are doing. We are tying everything together here, and yeah, this is the most general thing, the most general description of what I'm doing. Like, the context for data modeling of field bus systems is security analysis, and the goal is to create a data model that not only describes physical field bus systems but also give us better security analysis, and of course the target systems being field bus systems. Yep. That's it from my side. That concludes this talk, and yeah, now we move on to the question part. So these are a few questions for you. Like, think about it. It's very general. We don't have to go too technical about it. You can just think about it. You can come up with some ideas. If you want some more detailed information also about this before the talk, then you can obviously contact me on the email address given on the first page. And yeah, good luck, and see you later.